Have you ever wondered if the size of your bowl affects how much you eat? Let's take a look at how we can compute a theory-based p-value to address this research question. Do people eat more from large bowls? In this study, 17 students were offered M&Ms from either a large bowl or a small bowl. And on a different day, each of those students was offered M&Ms from the other bowl, and the number of M&Ms they took each time was recorded. Take a moment to think about how you would write out the null and alternative hypotheses for this study. Our null hypothesis is that mu sub d equals 0, where mu sub d is the mean of the differences, say small minus large, of M&Ms taken by every student in the population, not just these 17 students. Our alternative hypothesis is that mu sub d is less than 0. In other words, that on average, people take more M&Ms from the large bowl. In words, our null hypothesis would be that there is no association between bowl size and how many M&Ms people eat. Our alternative hypothesis would be that, on average, people take more M&Ms from large bowls. To find a theory-based p-value or confidence interval for paired data, we'll use a paired t-test or a paired t-interval. Our strategy here will be to first take the differences. In this study, we'll take the number of M&Ms from the small bowl minus the number of M&Ms from the large bowl for each person. Then we'll check the validity conditions for a one-sample t-test on the differences. So we either need the differences to have a symmetric distribution, or we need there to be at least 20 differences and have them not be strongly skewed. If the validity conditions are okay, then we'll use a one-sample t-test or a one-sample t-interval on the differences. For our M&M study, there were 17 students, so our sample size is less than 20. That means we should check whether the data are symmetric. One way to do that is to check if the data are normally distributed, using normal probability plots. Here, we see that the number of M&Ms taken from the small bowl is not approximately normal, because the normal probability plot for the small bowl, shown on top here, has points outside of the curved lines. But for a paired t-test, it's okay for the measurements in the two treatment groups to be non-symmetric, as long as the differences are symmetric. So what we really want to check is the normal probability plot of the differences after we subtract small minus large. And these do turn out to be approximately normally distributed. So we're okay to go ahead with a paired t-test. To do a paired t-test, we'll use the t-test function on our calculators, just like if we were doing a one-sample t-test. But the information we'll enter in will be about the differences, not about the raw data. That means we need to find x bar, the sample mean, and s sub x, the sample standard deviation, of the differences. There are several ways we can do this. One way is with the matched pairs applet. Without doing any randomization, so just looking on the left-hand side of the applet, we can look at the graph of the differences. In the upper right-hand corner of the graph, we can see that the mean of the differences is negative 10.882, so that's x bar, and the standard deviation is 36.301, so that's s sub x. Another way we can get the mean and standard deviation of the differences is with our calculators. We can start by going to Stat Edit and then entering the data from the two treatments, the small bowl and the large bowl, into two of the columns, say L1 and L2. Then we can use the arrow keys to highlight the L3 at the top of the next column and enter a formula to compute the differences. So type in L1 minus L2 using the second key and the numbers 1 and 2 to get L1 and L2. And then press enter. This will automatically fill in column L3 with the differences of L1 minus L2. Then you can use stat calc one variable statistics with L3 to find the mean and standard deviation of that column. The third way to find the mean and standard deviation of the differences is with Excel.
Let's see how to compute the mean and standard deviation of the differences in Excel. Here I have the data of the number of M&Ms that people took from the small bowl and the large bowl in two different columns. So each row here is one student. I'm going to create a third column called DIFF for differences. And then I'm going to click in cell C2 here, so the first cell in the differences column. I'll type an equal sign to tell Excel to get ready for an equation. And then I'll click on the cell that I want to use in the equation. So for this first row, I want to compute the difference 33 minus 41. And Excel is filling this in with the letter and number of the cells that I'm subtracting. And I'll press enter, and it does that computation for me. So 33 minus 41 is negative 8. Next, I'll click back on that cell and hover over the lower right-hand corner of the cell and drag it downward. Excel will fill in the formulas for each of those cells, automatically changing the formula to match the row and column that I'm currently in. So notice that the formula for entry C3 here is A3 minus B3. All right, so now I have the differences. I want to compute their mean and standard deviation. So I'll come down here to a fresh space in my spreadsheet, and first I'll compute the mean. So here's my label of what this is going to be. And then I'll click in a fresh cell where I want to compute the mean, type an equal sign again to get ready for a formula, and this time I'll type average, all capital letters, followed by parentheses. I want to compute the average of all of the cells in column C, from C2 down to C18. So I can click and drag to highlight all of those cells. And then I'll press a close parenthesis to finish off the set of values I want to compute the average of. And I'll press enter. That tells me that the mean is negative 10.882, the same value as we got from the matched pairs applet. Finally, let's compute the standard deviation. So I'm clicking in a new cell, pressing equals, and I'm going to use the same process I did for the mean, but instead of using the average function, I'm going to use the stdev .s function. So that's the standard deviation of a sample, because we only have 17 students here, not the entire population. So again, I've highlighted all of the columns, C2 through C18. I'll put a close parenthesis in and then press enter. And this has computed the standard deviation for us, which agrees with the matched pairs applet. Rounded to 3 decimal places, we have a standard deviation of 36.301.
Now that we have the sample mean and standard deviation of the differences, we can use them to compute a paired t-test. This uses the t-test function on our calculator. X bar and S sub x will be the values we just computed. N will be the sample size, in this case 17, and mu sub 0 will be the value from the null hypothesis. For a paired t-test, this is pretty much always 0. Give this a try on your calculator now. You should get a p-value of 0.117. This is a pretty large p-value, so our conclusion would be there is not much evidence that the number of M&Ms taken is associated with the size of the bowl. Or we could say it is plausible that, on average, people take the same number of M&Ms from large and small bowls. To compute a confidence interval for mu sub d, the mean difference, small minus large, we can use a t-interval, that is a one-sample t-interval, but applied to the differences rather than the raw data. Give this a try now. You should find that a 95% confidence interval is from negative 29.55 to positive 7.7823. Notice that this contains 0. That tells us that 0 is a plausible value for the average difference, small minus large. And that agrees with the fact that we found that the null hypothesis mu sub d equal to 0 had a p-value larger than 0.05.